LNG Aquarius, Aries, Capricorn, Gemini. Unusual vessels with a special mission: the safe, reliable, economical transportation of liquefied natural gas from remote sources of supply to the industrialized regions of the world. These liquefied natural gas carriers are the first of a series of essentially identical vessels being built by General Dynamics. They are super safe, reliable, built to the highest standards of quality. With a cargo capacity of 125,000 cubic meters, these ships are vitally needed for rapidly developing LNG importation projects. The potential demand for such ships became evident nearly a decade ago, and General Dynamics began a novel and innovative program to adapt its shipbuilding facility at Quincy, Massachusetts, for the specialized production of LNG ships. Series production was the goal, a concept requiring, first of all, new construction orders for a quantity of essentially identical vessels, and secondly, a design for those ships that would effectively standardize a substantial portion of the ship structure. General Dynamics designed a ship that would accommodate 5 identical cargo spheres. Fabrication of spheres could easily be standardized, and the spheres themselves could be built independently and simultaneously with ship construction. Next, the ship's hull structure itself was analyzed to achieve a structural design that would enable maximum practical use of standard parts and flat panels. The result? Over 60% of the shell structure could be so standardized. At the final stage of construction, with the ship's hull complete, the cargo spheres would be delivered to Quincy and installed one at a time, along with other pre-assembled components, to complete the ship. Series production, incorporating maximum practical standardization in the design for a multiple ship construction program, was achievable. When the first orders for LNG ships were received in 1972, a $70 million facilities modernization and retooling was well underway at Quincy, where the ships would be built. And near Charleston, South Carolina, a brand new $100 million facility was designed, built, and put into operation in just 2 years to build the 120-foot diameter all-aluminum cargo spheres. The hull is erected from large structural units assembled from standard machine-produced parts. Steel plate, standardized at 88.5 inches wide, became the basic structural element of the ship design. Longitudinal angles, spaced exactly 29.5 inches apart, form flat, stiffened plates. Several stiffened plates are then joined, forming larger panels, and webs are added for transverse stiffening of the panel. Flat sections like these are typical and the most common. Another standard panel is applied to the webs to form a basic unit or building block of the ship. These basic units are then joined with others, pre-outfitted with piping, ventilation, and electrical runs, and erected on the ship. The practice of assembling standard units off the ship and installing them later in a pre-planned hull erection sequence is a key factor in the successful series method of construction. Series production begins with the mechanized fabrication of the great quantity of basic structural steel parts and shapes common throughout the ship's standardized structure. Steel process lines are fed plate stock by 2 electromagnetic cranes servicing a conveyor system. Plates are inventoried by size and grade, loaded onto a conveyor system, and moved through de-icing and blast facilities directly into a huge fabrication shop. Here, highly mechanized and automated cutting and welding equipment is arranged in efficient, continuous processing lines, through which steel moves in progressively advanced stages of fabrication and sub-assembly. In preparation for stiffening, a standard plate is flame planed automatically to exact dimensional size, 88.5 inches wide, with edges beveled for welding. Meanwhile, other plates are conveyed to a flat bar stripper, whose 15 cutting torches set at exactly 6¼ inch intervals strip the plate into standard width bars used in nearly all stiffening members throughout the ship as angles, T-beams, and web stiffeners. Flat bars used for angles are arranged on a standard 88.5 inch wide plate, then fed into an angle fabricator. 6 pairs of fixed, submerged arc welding torches automatically weld the bars to the plate at preset intervals. Automatic post-heating and spray quenching prevents plate distortion. After bars have been welded to the plate, automatic torches cut the plate, forming multiple standard size angles. Elsewhere, a T-beam fabricator welds webs to flat bars to form T-beams. These T-shaped structural stiffeners are used in structural units and on watertight bulkheads. At the plate stiffening machine, up to 3 standard size angles are automatically welded to a plate previously sized and beveled by the flame planer. 3 pairs of submerged arc torches weld angles to the plate at exact 29.5 inch intervals, the standard stiffener spacing interval occurring throughout the ship. The product, a standard stiffened plate, typical of over 60% of the ship's structure. Irregularly shaped parts have been translated into Autocon numerical control data, then laid out and verified by an automatic drafting machine. Autocon tapes are fed into large numerically controlled automatic burning machines, which cut identical parts to precise dimensions from up to 4 plates at one time. Numerical control programs also operate a special machine for cutting the transverse stiffening webs. Here, 19 torches fixed at 29.5 inch intervals simultaneously make precisely shaped cutouts in the web for intersecting angle or T-beam stiffeners. Electromagnetic cranes and conveyor systems used throughout the shop maintain a continuous production flow. After cutting, the webs themselves are stiffened, using flat bars welded vertically between each stiffener cutout. Here again, the submerged arc welding process produces the superior weld quality achieved throughout the shop. Meanwhile, in another bay of the shop, the process of joining standard parts begins on the automated panel assembly line. Here, up to 4 stiffened plates are welded together into panels. 2 flux copper-backed, one-sided submerged arc welding machines weld 2 plate seams simultaneously. The twin panel welding heads are spaced exactly 88.5 inches apart, the width of a standard plate. Only 1 pass is needed for steel up to 1 1/4 inches thick, a highly productive application of advanced one-sided welding technology. At the other end of the panel line, pre-stiffened webs are set at position and welded at standard spacing intervals. The final product of the fabrication shop, web-stiffened panels, ready for assembly into larger structural units in outside platen areas. Standardized parts and subassemblies, fabricated with mechanized and automated equipment, ensure consistent dimensional control and superior structural quality throughout the following hull erection sequence. After welding, subassemblies are shot blasted and painted before being moved to outside platen areas where the large structural units are assembled. The various sections of the platen areas are fixtured for assembly of specific units. Curved sections are assembled on special cradles, flat sections on aligning stanchions. Production crews work repetitively on the same units from ship to ship. Familiarity improves both production and quality. Automatic one-sided gas metal arc welding is used for all full penetration plate butt welds. While structural work progresses, assemblies of cryogenic piping for the LNG cargo system are being fabricated in the pipe shop. The capability to weld square butt pipe joints greatly reduces fit-up time, and fully automatic welding for 90% of cryogenic pipe joints in both stainless steel and aluminum consistently produces the extremely high-quality weldments required for cryogenic service. The entire piping assembly comprising the compressor room is prefabricated and assembled in the pipe shop. After its structural enclosure has been added, the compressor room will be installed as a single unit. Smaller ship system piping subassemblies, also prefabricated in the pipe shop, are installed in structural units in the platen area prior to shipboard erection. Now, completed pre-outfitted structural units are given a touch-up blast and paint, then moved by transporter to the building basins. There, some units are joined with others, forming still larger assemblies, to minimize shipboard fit-up and welding time. To a carefully planned schedule, structural units weighing up to 190 tons are lifted into the building basin and erected on the ship. The hull erection plan, a building block sequence of standardized, pre-outfitted, and very large structural units, progressively fabricated and assembled, greatly improves control over fit-up and substantially shortens building time in the basins. In the cargo hold, a track-mounted automatic welding machine makes vertical welds in the seams of the steel skirt which supports the cargo sphere. With one-sided welding and automatic delta oscillation, only 3 or 4 passes are needed to complete vertical weldments in 1 1/4 inch thick steel. Weldments that meet the strict quality requirements for low-temperature service. 70% of all full penetration butt welds are made automatically using the one-sided welding process. The sequence for erecting hulls and completing ships in the waterfront facilities is the culmination of a carefully integrated manufacturing plan conceived to maintain a ship construction schedule synchronized with delivery of the cargo spheres from Charleston. The major hull erection work is done in 2 shallow water construction basins. Work is sequenced so that when one hull is half complete, another is being started in the opposite basin. When a hull is completed, it is first moved to an outfitting pier for ballast tank testing, outfitting, and preparation for sphere loading. In its place in the building basin, a new hull has begun. The ship is then floated into the larger assembly basin beneath the Goliath gantry crane. Here, the 5 cargo spheres, the bow section, and other large components are installed. Simultaneously, the next hull is moved from the building basin to the outfitting pier. After the cargo system has been installed, the ship is essentially complete. It is moved to the wet berth for system testing and preparation for sea trials. While the ships are under construction at Quincy, the cargo spheres are simultaneously being manufactured at General Dynamics' Sphere Building Facility near Charleston, South Carolina. In standardizing the ship for series production, a primary goal had been the manufacture of the cargo spheres independently, off-hull, and simultaneously with ship construction. A pioneering concept in shipbuilding, and a formidable challenge. Success depended on the ability to maintain the precise spherical shape so essential to the structural integrity of the spheres, and to achieve uniformly tight fit-up tolerances required for defect-free welding. To achieve these goals, plates of aluminum alloy, the basic elements of the spherical shell, are precisely formed and milled to exact spherical shape and size. These are then assembled on a rigid fixture with support and aligning features that establish and maintain exact sphericity during all stages of assembly. Assembly of the spherical shell begins as 2 identical plates are welded together on unique tilting cradles, which enable outside and inside welds to be made, each in a single pass, using high current density MIG welding. For main assembly, the 2-plate shell sections go to the Mammoth Assembly Hall, housing 6 unique fixtures for the simultaneous erection of 6 spheres. Assembly proceeds from a central equatorial ring, the only stiffening member required in the sphere structure. The lower hemisphere is assembled downward from the equatorial ring. First, the tapered plates are installed. Then, the lower, non-tapered polar plates with precise plate alignment. When the lower hemisphere is complete, external and internal welding gantries positioned along each seam carry self-propelled welding carriages which traverse the inside and outside of the seam. Automatic oscillating welding heads will lay over 50 miles of welding passes to join the 42 2-plate subassemblies comprising each sphere. And while assembling and welding of the lower hemisphere progresses, internal fixturing is installed, with its staging extended to support assembly of the upper hemisphere. Immediately after welding, every inch of weld is radiographed automatically by equipment mounted on the welding gantry tracks. After the lower hemisphere has been assembled, assembly of the upper hemisphere begins, while welding and radiography continues. The successful use of a high current density gas metal arc welding process has been the single most important factor contributing to the high productive capacity of the facility. Precision forming and fabrication processes, assembly on rigid fixtures, and the automatic high-energy welding of aluminum have enabled General Dynamics to achieve the unique capability to produce in series these huge aluminum LNG cargo tanks. Supported on 3 translift units, the complete sphere is walked from the assembly hall to a test stand for leakage tests, then to an insulation building, where an 8.5-inch blanket of insulation is applied over the entire surface and is sealed with a protective coating of sprayed urethane. Now, the finished sphere is loaded aboard a special ocean-going barge designed and built by General Dynamics for the 900-mile voyage to the shipyard at Quincy. Traveling at an average speed of 10 knots, the passage to Quincy takes about 4 days under moderate sea conditions. Arriving at Quincy, the barge is landed in a basin next to the ship, and the 800-ton sphere is lifted into the ship by the 1,200-ton Goliath crane, largest of its kind in the Western Hemisphere. Spheres arrive at Quincy and are installed in the ship at 3.5-week intervals. Now, nearly complete, the ship is moved from the assembly basin to a wet berth, where final piping, painting, and interior finishing is accomplished, and the ship and its cargo system are thoroughly tested. Ready for sea, the ship departs on builder's trials, a completed LNG tanker, as technologically complex as any merchant ship afloat, yet designed and structurally standardized for efficient, modern shipbuilding as few sophisticated vessels ever have been. Safe, reliable, possessed of the highest structural quality, a product of General Dynamics.